Have you ever looked up at the night sky? Have you ever seen that faint milky band of light stretching across the darkness? That is our home. That is the Milky Way galaxy. It's a vast, sprawling city of stars, dust, and gas. And we live on a tiny blue planet tucked away in one of its spiral arms. But here is a thought that might keep you awake. Can we ever leave? Can humanity ever venture beyond the confines of our own galaxy and journey into the true deep blackness between the galaxies? It's a question that challenges the very limits of our technology, our ambition, and even our understanding of the universe itself. Our galaxy is an immense structure. It's a place of breathtaking beauty and scale. It contains hundreds of billions of stars, perhaps even trillions of planets. Light itself, the fastest thing we know, takes about 100,000 years to travel from one side of the Milky Way to the other. Think about that for a moment. The light from stars on the far side of our galaxy began its journey towards us when our distant ancestors were first learning to use tools, long before the rise of civilization. This scale is almost impossible for our minds to truly grasp. We are inhabitants of an island of light, surrounded by an ocean of nothingness. The Milky Way is our cosmic neighborhood, but it is a neighborhood of unimaginable size. Imagine it as a gigantic, spinning disk of stars. Our sun is just one of at least 100 billion stars swirling around a supermassive black hole at the galactic center. This disk is so vast that if you could travel at the speed of light, it would still take you 100,000 years to cross from one edge to the other. Our entire solar system is a mere speck of dust within this structure, orbiting the galactic core once every 230 million years. The last time we were in this part of the galaxy, dinosaurs were just beginning to roam the Earth. This scale presents the ultimate barrier to exploration. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object. After more than 4 decades of travel, it has only just left the protective bubble of our sun, an area we call the heliosphere, and entered interstellar space. Yet it is still nowhere near leaving the galaxy. To reach the very nearest star to our own, Proxima Centauri, would take Voyager over 70,000 years. This isn't a limitation of our engineering, it is a fundamental limitation imposed by the laws of physics and the sheer crushing emptiness of space. We are like ants on a very large dinner plate, able to crawl around our immediate vicinity but with no realistic hope of ever reaching the other side of the table, let alone the next room. What exactly is a wormhole? The idea comes from one of the most successful theories ever conceived, Einstein's general theory of relativity. Einstein showed us that space and time are not separate things. They are woven together into a single, four-dimensional fabric called space-time. He also showed that massive objects like stars and planets warp or curve this fabric. It is this curvature that we experience as gravity. A planet orbits a star not because it is being pulled by an invisible force, but because it is following the curve in space-time created by the star's mass, like a marble rolling around a dip in a rubber sheet. This is where the idea of a wormhole, or what scientists first called an Einstein-Rosen bridge, is born. The theory suggests that it might be possible for space-time to be curved so extremely that it folds back on itself, creating a tunnel. Imagine that rubber sheet again. If you wanted to get from one point on the sheet to another, you would have to travel across the surface. But what if you could poke a hole through the sheet and connect it to another point? You would have created a shortcut, a tunnel that dramatically reduces the travel distance. A wormhole is the cosmic equivalent of this. In theory, a wormhole would have 2 mouths connected by a single throat. You could enter one mouth and instead of traveling the millions of light years across normal space, you would pass through the throat and emerge almost instantaneously from the other mouth in a completely different part of the universe. It could be on the other side of our galaxy, or even in another galaxy entirely. It would be the ultimate cosmic shortcut. It would not be about traveling faster than light, but about making the journey itself profoundly shorter. However, there is a very big problem. According to the mathematics, these simple Einstein-Rosen bridges are incredibly unstable. They would snap shut the instant anything tried to pass through them. To create a stable, traversable wormhole, we would need something truly exotic. To keep a wormhole open, to prop its throat open long enough for something to pass through, you would need something that has negative energy or negative mass. Scientists call this exotic matter. This is not like anything we have ever discovered. All the matter we know, from the atoms in your body to the stars in the sky, has positive energy and creates a positive gravitational pull. It pulls things together. Exotic matter would do the opposite. It would have a kind of anti-gravity. It would push space-time apart, and this repulsive force is exactly what you would need to stop a wormhole from collapsing in on itself. So, how does this compare to other ideas for interstellar travel? The most familiar concept is the Starship, a vessel that travels through space using powerful engines. We are already building this technology, albeit on a very small scale. But as we have seen, even with hypothetical fusion rockets or solar sails, the journeys between stars, let alone galaxies, would take many thousands or even millions of years. A wormhole is fundamentally different. It is not a vehicle, it is a destination. It is a piece of infrastructure. It is less like a ship crossing the ocean and more like a bridge built over it. The potential rewards are astronomical. With a stable wormhole, the journey to the Andromeda Galaxy could be reduced from 2.5 million years to a matter of minutes or hours. We could establish a network of these tunnels, connecting star systems and galaxies like a cosmic subway system. It would open up the entire universe to exploration and perhaps even colonization. The vast empty distances that have imprisoned us for so long would suddenly become irrelevant. We would transition from being a species confined to one planet to a truly galactic civilization, with access to countless new worlds. But the risks and unknowns are just as immense. We do not know if exotic matter is even real. It is a theoretical requirement, but it may not exist in nature, or we may never discover how to create it. And even if we could build a wormhole, what would it be like to travel through one? The intense gravitational forces and radiation inside the throat could be instantly lethal. And there is the question of where the other end might go. Could we control the destination, or would we be opening a random door to an unknown and potentially hostile part of the universe? So, are wormholes our ticket out of the Milky Way? The honest answer for now is that we simply do not know. The concept rests at the very edge of our understanding of the universe. It is a beautiful mathematical possibility born from our best theory of gravity, but it remains purely theoretical. We have never seen one. We have no idea how to build one. And the one ingredient we think we need, exotic matter, might be nothing more than a ghost in our equations. The challenges are enormous, perhaps even insurmountable, but we should not let that discourage us. Every great leap in human history began as an impossible dream. There was a time when crossing an ocean was a near-certain death sentence, when flying was the stuff of fantasy, and when traveling to the moon was pure science fiction. We solved those challenges not by giving up, but by being curious, by being persistent, and by pushing the boundaries of science and engineering. The quest to understand wormholes is part of that same grand tradition of human curiosity. It forces us to ask the biggest questions. Even if we never build a wormhole, the search itself is valuable. In trying to understand these extreme possibilities, we learn more about the fundamental nature of space-time, gravity, and the universe we inhabit. The pursuit of these grand ideas can lead to unexpected discoveries in other areas, from energy to computing. It is by reaching for the stars that we often solve our problems here on Earth. The journey of discovery is just as important as the destination, and the knowledge we gain along the way enriches us all, expanding our perspective on the cosmos. The future of humanity among the stars is unwritten. We are a young species, and our science is younger still. What seems impossible to us today may be commonplace for our descendants 1,000 years from now. Perhaps they will find a way to create exotic matter. Perhaps they will discover that wormholes occur naturally, or perhaps they will find an entirely new method of travel that we cannot even begin to imagine. The universe is a vast and mysterious place, full of wonders yet to be discovered, and as long as we keep looking up, as long as we keep asking what if, there is always hope.